Good morning, good morning, good morning. How is everybody doing today? Super excited because you can see me now. All right, and since you can, I'm going to point out that the translation of the elements that we've been using, this is, of course, the beginning of session 5, is this translation by Sir Thomas Heath. So this is the translation of the elements that I've been using for this class. All right, that said, let's get into this. All right, so we are on session 5 of Euclid's Elements, and we will be finishing the definitions today. Just for the sake of review, so far we have said that a point is that which has no part. We said that a line is length without width. All right, so you take a point, it is location without any length, width, or depth. You give it length, and you have a line. You still have no width or depth. And then the extremities of a line are points, and a straight line is one that lies evenly with all the points on itself. After that, we said that a surface is that which has length and width. So you take a point, you add length, you have a line. You take a line, you add width, you have a surface. And since the extremities of a line are points, the extremities of a surface are lines. Then we said a plane surface is a surface where all the lines lie evenly with all the other straight lines on itself, kind of following the pattern that we had with the straight line. We said then that a plane angle is just the inclination to one another of two lines that meet in a plane. That a rectilineal angle is a plane angle where the lines are straight. We said that when you take one straight line, you set it up on another straight line in such a way that the two lines, that the angle on either side of the line, that they're equal to each other. Then you call those angles right angles, and those lines are perpendicular. We said that an obtuse angle is an angle greater than a right angle, so that's the A here, angle A here. And we said that an acute angle is an angle smaller than a right angle, so that's the angle B here. We said that a boundary is just the extremity of anything, so we just gave a special name to extremities. We call them boundaries. We said that a figure is anything contained by a boundary or multiple boundaries. We said that a circle is a plane figure contained by one line, a single line, in such a way that all of the straight lines falling on that straight line, that boundary, from one point lying within those are equal to one another. That is, a circle is a very, very special kind of figure. It's the only figure that has this interesting property of having a point in it from which, if you draw from a line from that point to the boundary, all of those lines will be equal. So that's neat. The center of the circle is that point, and we said that the diameter of a circle is any straight line drawn straight through a straight line that goes through that point and hits the boundary twice. Then we said if you take that diameter and you make a figure out of it and the part of the circle on one side or the other of it, you have a semicircle. And interestingly, the center of the semicircle is the same as that of the circle. So the center of a semicircle is not in the middle of the semicircle, and I mentioned that might be frustrating, but we're going to keep moving on. After that, we really quickly defined rectilineal, trilateral, quadrilateral, and multilateral figures, and that was fairly straightforward. We just noticed that rectilineal figures are ones controlled by straight lines. Plane trilaterals are three straight lines, quadrilaterals are four straight lines, and multilateral are more than four straight lines. Then we said equilateral, isosceles, and scalene triangles are, and we defined those. An equilateral triangle is one where all the sides are equal. A scalene triangle, an isosceles triangle, is one where two sides are equal. And a scalene triangle is one where none of the sides are equal. And that is as far as we got. So it's now time to move on to definition 21. Very exciting, I know. All right, definition 21 is the definition of a right angle. I'm even waiting for this one. Right angle triangles. And also, because again, we're at that point that Euclid is cramming lots and lots of terms into each of his official definitions. So we have right angle triangles. We also have obtuse angled triangles. Obtuse angle. Oh, and a capital A on that. Obtuse angle triangles. And let's see, anything else. And acute angle triangles, which I should have predicted anyway. They're acute angle triangles. And since we have an and there, I'm going to change that comma to an and sign. There you go. Obtuse angle and acute angle triangles. So right angle, obtuse angle, and acute angle triangles. And because I also like the Oxford comma, I'm going to put it back. Okay. So how do we actually define how does Euclid define these? Okay, so he says further, this is following on from definition 20, of trilateral figures. So now remember that we talked about trilaterals and all the rest of that. Of trilateral figures, I didn't finish writing. Trilateral figures, comma, a right angle, right angle, I cannot type today. A right angle triangle is that which has a right angle. Yay! I love it when definitions are straightforward and easy. And this is going to make the rest of them pretty easy too, by the way. Obtuse angle triangle. But just because they're easy doesn't mean they're not important. Obtuse angle triangle, that, I wrote triangle, triangle, an obtuse angle triangle, that which has an obtuse angle, and an acute angle triangle, that which has its three angles acute. So all three of the angles have to be acute in an acute angle triangle. So let's take a look at these and see what they would look like. Okay, so let's make these triangles, shall we? And I have to remember that I can't use, that my face is hanging out down here. Y'all can't tell it, but in the recording that I'm making, I can't see my face down here, but I remember that I put it there. So I have to leave that space empty, and I'm sorry if that sort of messed you up earlier with the review. I'm going to try to avoid doing that in the future. Okay, so let's make our triangle. So first off, we need a right angle triangle, and to do that, it needs to have a right angle in it. Fortunately, PowerPoint here allows, I think right angle triangles is sort of one of the things it has pre-packaged for me. It does. Here is a right triangle, which is what we tend to call these things these days. All right, so there's a right triangle. And since I'm a big fan of green triangles, I just sort of believe all triangles should be green, deep in my bones. Let's do that. Remember, we don't believe in outlines, so here we go. There is our right angle triangle, and we know that this is a right angle triangle because, well, we know it right now because PowerPoint said it's a right angle triangle when I chose it. But if we want to do that properly and geometrically, the way we would do that is pretty cool. Let's see if we can do this. So here's our right angle triangle. We're going to play with it here. So I'm going to put it off to the side so I can prove to you that it's a right angle triangle. So let's take a line. Here's a straight line, and let's copy it. First, let's do that. There we go. And now we're going to do another straight line, but this one is going to be set up on it, just the way we were taught. So there we go. And let's put those together. We're going to root. I'm going to move this line before I root them. Oh, they're already grouped. Okay. Just want this one. There we go. All right, perfect. I have to group them again now. Group those. Okay, so there we go. Now, we know that since this is a perpendicular line, then these two angles then therefore are equal because we did that. And look at that. The angle is indeed, right? Boom, boom. Look at that. That's a right triangle. And we know that because what we can do is copy and paste. And I think I can just rotate it. There we go. And now it's not going to be the same size, but what I wanted to do is flip it. But you'll notice that that angle and that angle together is still a flat line. So therefore, we have a right angle. So yay, it's a right angle. It's a right angle triangle. Because together the angles in here, this is the same angle, by the way, you'll notice. Right, so keep an eye on it just so so it doesn't look like I'm pulling the wool over your eyes. I want to prove this to you properly. So here we go. Here's our angle, our triangle. Remember, I haven't made it bigger or smaller or changed it at all. You saw me copy and paste it, so you know it's the same angle. You know it's the same triangle. All I'm going to do here is I'm going to rotate it. Keep your eye on the angle that we're talking about. We're talking about this angle down here. So I'm going to rotate it through until it's all right. There we go. And now so that same angle, when I add it to itself, right? When I put that angle next to itself, right? It forms one exact line, so it's equal. So therefore, you know that the two angles are equal, and that's all we needed, because if those two angles on either side of a perpendicular are equal, you know that it's a right angle. So that's a right angle triangle, and we know it's a right angle triangle, and we feel very good about it being a right angle triangle. So there we go. There's our right angle triangle. Let's go ahead and give it itself. There we go. Take a word box here. It's not going to be plain figure, obviously, but let's go ahead and just steal our word box, and we will just say that this is a right angle triangle. Right angle triangle. By the way, people today, as in people after Euclid, have taken to just calling these right triangles, and that's probably what you heard it called in school if you did right triangles in school. Let's move this whole shebang all the way over here to make myself a little bit of extra room. So there's our right angle triangle. Next, we need an obtuse angle triangle. So an obtuse angle triangle is one that has an obtuse angle. So for that, obviously, I'm not going to be allowed to use a right triangle, because a right triangle doesn't have an obtuse angle in it. We will prove that later on, but for right now, I'm just going to have to ask you to trust me. So let's go ahead and grab ourselves a triangle that can become obtuse. That's an isosceles. Oh, I had to make an obtuse angle, didn't I? All right, so let's make an obtuse angle triangle. That's a flowchart. And I did that with my draw your own shape tool, if I remember correctly. So where is my draw your own shape tool? It would be good if I had these sort of pre-picked out. Come here, draw your own shape tool. Insert shapes. Where's my draw your own shape tool? Here it is. Okay. So we need an obtuse triangle. So let's make an obtuse triangle. We know it's obtuse if I go this way, before I go this way, before I go that way. That way we know that that angle is obtuse. All right. So there we go. There's our obtuse angle. This is more than, see, we can just put it on this here. Yeah, we'll rotate it just a hair so that it's sitting flat on. All right, it's close. Anyway, you can tell, because it's not sitting quite right, but you can tell this is certainly more than, it's bigger. This angle right here is bigger than a right angle, and from here you'll remember that, or actually from all the way up in the definition here, an obtuse angle is an angle greater than a right angle, and we now know, because we just sat it on there and compared it, that this angle is greater than a right angle. So therefore, this is an obtuse angle triangle. So let's copy our word box, pop it over here, and this is an obtuse angle triangle. Capitalize obtuse just to make this all work. Okay. I'm going to have to move it on over here and crowd my right angle triangle just a little bit, because I want to fit things, and I just remembered that my face is hanging out down the bottom right corner. We need an acute angle triangle, and let's do that real quick. We're going to do it by making one on here again. There are other ways to do it, but an isosceles triangle is technically acute, but we're not going to do it that way. We are going to do another make your own shape tool, and let's make it on this thing. So we need an acute angle triangle. So here's part of the line, and then I'm just going to do this angle here, and I'm going to do down here, and there we go. My shape isn't complete because I didn't complete it right, so let's try that again. Let's do this right. All right, so we'll make it first, and then I'll prove to you that it is obtuse, or that it's acute. It's such a cute angle. If I can find it, I might find my maker tool. Here we go. All right, so let's make an acute angle triangle. So I need a straight, flat line there, and then this would be sort of a right angle, right? So I'm gonna kind of go in from that, and then there we go. All right, now you notice that all it needs. Oh, I didn't make this green. Oh, we can't have non-green triangles. And I even left its outline. I am getting sloppy. There we go. And we're gonna make this one is gonna be our sort of awkward greeny color. I'm colorblind. Don't judge me. No outline. Here we go. Okay, so we know that this is. Here we go. See, look. So we can put this the bottom of it on this line, and since we know that's a right angle, we can see that this is less than it. So this angle is less than a right angle. Therefore, ta-da! That angle is acute. Now, it has to have 3 angles acute, though. So let's check to make sure the other 2 are acute. Put this next one on there, compare it to our right angle triangle, and look at that. It is acute. And we got one more to do. Look at that last one, and let's put it on there, and look at that. It is also acute. So notice that, and this is an interesting thing about this. I'll go ahead and rotate this around the rest of the way. But I want to go back to our definitions here in just a second. First, let's go ahead and label this one. All right, move this over here to make sure this is an acute. It's an acute angle triangle. All right, now I want you to notice something interesting about this one, about the definitions here. So for a right angle triangle, it only has to have a right angle. You only have to have one right angle to be a right angle triangle. An obtuse angle triangle only has to have an. That means it only has to have one obtuse angle. But an acute angle triangle has to have 3 acute angles. Just notice that, and we're going to think about it later on. Okay, let's move on to definition 22. There are only 23 definitions, so we're only 2 away here. Definition 22 is the definition of, take a deep breath, because actually it's a definition of a lot of things. A square, yay, I know you've been waiting for squares. A square, an oblong, should have a capital O there. Square, and you know what, I'm going to get rid of the ands here. Squares, square, oblong. We're also going to define rhombus. Elementary school teachers, for some reason, really love rhombuses, as far as I can tell. Rhomboid. And, because that, as if that weren't enough, and trapezia. Trapezia, that's a plural, so there's more than one. These are trapezia. I guess a trapezium, I think would be the correct singular. All right, here we go. All right, so this is a long definition. Get ready. I'm probably going to end up shrinking the text a little bit just to make space for everything we want to do on this particular slide. Make the space. All right, so here we go. Of equilateral figures. So already we know that these have to be equilateral. Figures. A square. Sorry about that. Pause for half a second there. Or anyway, a square is. Oh, square is supposed to be italicized. A square is that which is both equilateral and right angled. Comma. No. Semicolon. An oblong is that which is right angled but not equilateral. Stick with me here. A rhombus, I just like that word, that which is equilateral but not right angled, and a rhomboid, yep, that which has its opposite sides and angles equal to one another, but is neither equilateral. Don't worry, we're going to get through this. I know this is really long, but don't worry, we'll get through it. And it's easy and kind of fun. It's sort of satisfying. Neither equilateral nor right angled. We'll get there. Don't worry. Neither equilateral nor right angled. And just because that wasn't quite enough, and let quadrilaterals other than these be called trapezia. And yes, quadrilaterals. There we go. Be called trapezia. All right. So, like I said, there's a lot there. Let's go ahead and we're just gonna shrink that. Come on, smaller. There we go. All right. So we're gonna fit all this in here. Okay, so we're going to work through these one at a time in the order that Euclid does. Now, but before we do, we have to recognize, I'm going to sort of own up to here, Euclid did not bother defining equilateral for us outside of equilateral triangles. He hasn't defined equilateral itself as a term. He sort of defined an equilateral triangle, but he didn't define just general equilateralness. Equilateralness means for any shape, any figure, the same thing it means for triangles. That is, all of the sides are equal. As long as all the sides are equal, the thing, whether it's a triangle or a quadrilateral or whatever, is equilateral. So we're talking about equilateral quadrilaterals so far. Okay, that's a square. Let's make a square. Squares are fun. Here is a rectangle, and is there a guaranteed square, or do I have to... You know what? Let's do it this way instead. Let's make a square that we can be certain is a square, because that's what we really want to do. So here's a square. Here's a line. So that's a line. We like lines. And now what we're going to do is we're going to make a square by copying it and rotating it. And I just realized that I haven't... You know what? I don't know if it stays the same or not when I rotate it. In fact, I know it doesn't have to, so that's not going to work. I was hoping I could just rotate it without letting it change its size, but I cannot do that. So I am not deterred. What I'm going to do now is I'm going to make you an equilateral triangle. Here we go. I'm going to make another shape, a square that I can prove is equilateral. So we know we have equilateral triangles around here somewhere. We have right triangles. Okay, so here we go. Right triangles all I need. If I have a right triangle, I believe that's correct right there. All right, and then what I'm going to do is I'm going to, let's go ahead and, you know what, let's change things up. I want to change things up. I'm going to fill this one with, I want to make it black. It's not black. I want black. There we go, black. And we don't believe in outlines, so still no outlines. And now I'm going to copy it, and I'm going to paste it. What I'm going to do is I'm going to just rotate it 180 degrees. And there is my square. Boom. Right? That's a square. And I know that's a square because I know that this angle is equal to, now this angle is equal to this angle is equal to this angle, and this line is equal to this line is equal to this line is equal to this line. I know that, well, and the angles actually technically I'm not supposed to know that. I'm cheating on that. But I know the lines are equal because this was an equilateral, well, I know I made the equilateral triangle that way. You saw the little dot, dot, dots. So these two lines are equal, and it's the same triangle, just rotated. So that means that these two lines are equal. So all the lines are equal to another, and that makes it a square. It is equilateral, and it is right-angled. So check and check. We know it's right-angled because because I used an equilateral triangle, which has right angles. All right. So in fact, let's see something really cool. So I'm going to group this, group those. And now I can just rotate it, and boom, it still keeps working. Still a square. Okay. Unhand my square. Okay. Next one. Oh, okay, so that is a square. And let's go ahead and put our definition terms here. So this, whoops, this is a square. This way, let's do that, let's center it, and no, I did not want to do that. I wanted to do this. Let's go ahead and group those and move that as far over here as I can so I have space for everything. Okay, an oblong is that which is right-angled but not equilateral. Those are easy. You usually think of them as rectangles, but Euclid wants to call them oblongs. So it's right-angled. These are just automatically right-angled. I'll prove that it's right-angled in a second, but not equilateral. Okay, so let's prove that it's right-angled, and we can do that by inserting our triangle right on top of it. And there's our triangle, and look, that's an equilateral triangle. We know that's an equilateral triangle, and look at that. It's sitting nicely on top of our oblong. Therefore, it's right-angled. Oh. So that's fun. Let's go ahead and make it red. There we go. And that is an oblong. Call it an oblong. So much fun was had by all. So there's our square, there's our oblong. It's right angled, but it's not equilateral. We know that because this is this side is longer than this side, right? The bottom and top are longer than the left and the right. A rhombus is that which is equilateral but not right angled. Those are fun. So a rhombus is basically the opposite of an oblong relative to a square. So a square needs to be both equilateral and right-angled. An oblong is right-angled, but not equilateral. And a rhombus is equilateral, but not right angled. Highlight my stuff here. So right angled, but not equilateral. Sorry about that buzzing. Hopefully it'll go away soon. It's getting a phone call, but I can't answer it right now. All right, so let's make a rhombus. I think they gave me a rhombus automatically if I want one. I think I have a free. I do have a free rhombus I can make. Here's my free rhombus. Okay, it's technically, I think it's more rhombusy. So here we go. I should just do it that way. Right, there we go. Rhombus. So this line needs to equal this line, and this line needs to equal this line, and they all need to equal each other. So if all these lines are the same length, then it's equilateral. But you'll notice that it's not right angled. We know it's not right angled because we can take it and compare it to our square and say, look, this angle is less than a right angle. And also we could rotate it because we want to have fun. Why? That was the wrong choice. We can rotate it to have fun and do it that way and say, look, now that angle is bigger than the right angle. So it is not right angled. There we go. So there we go. All right. That makes it a rhombus. A rhombus. Center. Let's shrink this a little bit. And I'll put that under here. There we go. All right, and let's just group those because that makes me feel good about my life. All right, those are grouped. And so rhombus is equilateral, but not right angled so far. And a rhomboid, sorry, I should highlight equilateral, is there. Right to yellow, but not, oh, it didn't, green. Equilateral, come on, equilateral, let's yellow up our equilateral. All right, so we said that our rhombus was equilateral, but not right angled. Forgot to do over here. All right, so there we go. And next up is the rhomboid, which has its opposite sides and angles equal to one another, but is neither equilateral nor right angled. So opposite sides need to be equal to each other, but it can't be equilateral and it can't be right angled. I'm not even sure if I can make one properly here, but let's do our best. I'm definitely going to need my free draw tool on this one. So we're making a rhomboid. So we need this angle. There we go. All right, so there's a line. So far, so good. Right? Its opposite sides and angles need to be equal to each other. So I'm going to do another line here. And it can't be right angled and it can't be equilateral. So it's not right angled now. And you know what I'm going to do is I'm going to make a triangle. I trust my triangles. And since it's a triangle, I'm working with the triangle. I'm working green here. Let's get rid of the outlines. No outlines. No outline. And now, all right, so far, all I know is I have, this is not equilateral. Right? It's not equilateral. Oh, sorry. Okay, so far. So now I need to finish this up. Let's try this again. So now I need to finish this up to make it a rhomboid. I need for opposite sides and angles. Let's work this. Opposite sides and angles equal to one another, but neither equilateral nor right. Okay, so yeah, so this is all. It's an sort of an oblong rhombus. So now I'm going to do is I'm going to copy it, I'm going to paste it, and then I'm going to do this. Same basic dealio I did with my. There we go. Same basic dealio I did with my square. Close it up, and there we go. So these are equal. These are equal. This is a cube. This is an obtuse angle right here. So it's not equilateral. It's not right angled. These are equal, and these are equal. But it's not. But all of the sides aren't equal with each other. Make my shape work here. Come on, shape. Oh, I'm on the wrong one. That's probably. That's it. Yeah, there we go. Okay, so since this side is not equal to this side, this is a rhomboid. Okay. If this side were the same length as that side, it would be a rhomboid, but it's not, so it's not. Okay. What do we have left? Oh, now we need trapezia. So trapezia, sorry, that which has its opposite sides and angles equal to another, but is neither equilateral nor right angled. So I just did that, and I undid it. Opposite sides and equals not right angled. Okay. Quadrilaterals, any quadrilateral that is not this is a trapezia. And to be a quadrilateral, all it needs, remember, is 4 sides. So those are really easy to do. Let's go ahead and make ourselves some kind of ugly quadrilateral. Here we go. A trapezoid. It's pre-made for me, all right? So not equal. All right, let's just check this. I need a different color. Let's fill this with ugly mustard. All right, ugly mustard color, no outline. Here we go. So let's just check this. Okay, so it has these sides are not equal, so it is not equilateral, because we already see 2 sides which are clearly not equal. Look, we can take these and say this one is larger than that side, and if we flip it, that one's smaller. So we know it's the sides aren't equal. Okay, so that's the first thing we need to worry about, and we have taken care of that. I think this, yeah, we can do that too. So actually, we could start with this. Look at that, it's a square, and now it's definitely not. Okay, so the sides aren't equal. It is therefore not equilateral. So it cannot be a rhombus. We know it's not a rhombus, and we know it's not a square. How do we know it's not a rhomboid? Well, that is an interesting question. It actually might be a rhomboid, so let me double check on here real quick. Equal to one another. Okay, opposite sides aren't equal to one another. See? So it's not a rhomboid because this side is opposite this side, and they're not equal to one another. So it's not a rhomboid either. Okay, so it's not a rhomboid, it's not a rhombus, it's not a square. Is it an oblong? Well, an oblong has to have right angles, and these, so let's check to see if this has right angles. This is definitely not a right angle. Look, it's smaller than the right angle of the oblong, so it is not right angled, so it's not an oblong, which means it's not one of those things, but it is 4-sided, therefore it is a trapezoid, or it's a trapezoid. A trapezoid. Trapezium. I still like trapezium, but that would be Latin. We're mixing up Latin and Greek. That was a mistake I made earlier. Trapezoid. Trapezoid. Here we go. All right. Ta-da! And now, take a deep breath. Here's definition 23. New slide. Definition 23 is the definition of parallel. Parallel straight lines. All right. Much grief is going to be shed over this definition and the next one. We're going to go ahead and do this. Okay, so here's Euclid's definition. Parallel, just remember I said about the grief because you're going to remember later on. Parallel straight lines are straight lines which being in the same plane, okay, so far we need to be in a plane, we'll get back to our plane now, and being produced indefinitely, I'll explain that word in a second, that means, well, I'll explain in a second, and being produced indefinitely in both directions, that's going to be important too, do not meet one another in either direction. He's just going to define this. This is just, remember, he doesn't need to prove it. He's just saying, this is what I'm talking about when I use this term. Okay, so what does he mean by this? Well, what Euclid is saying, he says, parallel straight lines are straight lines, which being in the same plane are produced indefinitely in both directions, do not meet one another in either direction. All right, let's define indefinitely here. Define indefinitely. Indefinitely means without an end. So produced forever in both directions, or without stopping, really, is what he means there. And they can't meet each other in either direction. So let's go ahead and do this. So let's take a straight line. Now, first we need a plane. Let's go ahead and grab a plane. We'll steal it from definition 18. Come here. Plane of definition 18. Here's our plane. I'm going to go ahead and shrink our plane because I've got to get out of my space. Okay, so here's our plane. Now, instead of a plane like this, we need to realize, oh my gosh, this plane won't work. Why won't this plane work? It won't work because you can't produce something indefinitely in this plane. You need an indefinitely large plane. You need a limitless, a plane without end, in order to produce lines indefinitely within it. So let's go ahead and say, oh, we thought we had a plane, but we actually need to make imagine a new plane. So let's imagine a new plane. I can make a plane that we can do indefinite, at least. Here we go. So there we go. And then we're going to copy that, and we're going to paste it, and we're going to move it down here, and we're going to say, look at that. That's a plane. Now, why is that a plane? Well, it doesn't have any boundaries on either of the two ends, so you're going to have to imagine it going on forever and ever. In fact, let's just do this so that you can make this. Here we go. So you can see that it just sort of starts off the screen on this end, and it keeps going, and the lower boundary starts off the screen on that end, and it keeps going. So it's a plane, but it's only got an upper and lower boundary. It doesn't have bottom or top boundaries. It doesn't have side boundaries. Okay, so parallel straight lines are straight lines which being in the same plane, so we're gonna let's make two straight lines in the same plane. We've got our plane now. Let's make some straight lines. All right, there's a straight line, and here's another one. All right, some straight lines. Straight lines, which being in the same plane are produced indefinitely in both directions and do not meet one another in either direction. So I'm going to make these lines look the way you want them to look. Here we go. There's two lines. Let's go ahead and go there. Here. Do this. Let's go ahead and make it red. And let's make it thicker just so you can see it properly. So there's a line. Of course, lines don't really have width, but we've done this. These are our fake lines that we're just making easy for ourselves. And that one will be blue, and we'll make it big and wide too. There we go. All right, so there's our two lines, but we have to produce them. Now, here's what Euclid wants us to do. He says if you take this line, right, and they're both in the same plane, but now I have to produce them infinitely. So I have to make this go infinitely, and then make this go infinitely. And now if I do that, then what I find is, boom, they met. Right? That's a problem, because that means they're not parallel. In order to be parallel lines, they have to, if produced infinitely, never meet. So how do we do that? Well, what we do, I hope for right now, and we're going to come back to this, I promise we'll end up having to come back to this and make you very miserable. But for right now, we're going to pretend that everything works and is happy. We're going to go ahead and make them both straight lines like this. I guarantee that they will be parallel by... I did a copy paste, but I won't do that. So now if we produce it infinitely in this direction, and we produce this one infinitely in this direction, and we produce this one infinitely in this direction, and we produce this one infinitely in this direction, look, they never meet. And we can do that. That'll be clearer and more understandable if I again go from here, and there we go. There they are, not meeting, and therefore they are, according to Euclid's definition 23, parallel straight lines. How do I know they'll never meet? Well, I kind of don't at this point. I'm going to sort of trust that these are parallel lines, because I can't draw these lines forever, right? I mean, we could sit here for the next 1,000 years and just keep making them longer and longer and longer. Maybe imagine yourself with a piece of paper that was endless, right? So it's an endless plane, and you start drawing a straight line on it, and you draw a second straight line on it, and you start drawing one, and you just draw it for 1,000 years, and then you take the next one and you draw it for 1,000 years, and after 1,000 years they still haven't met. Do you know that they'll never meet? You don't know that they never will meet, so you don't know whether they're parallel for sure. But if you've been going for 1,000 years and they haven't met, or don't even seem closer to together, you can feel confident that they probably won't meet. Now, there is a lot more that Euclid is going to have to say to this when we get to postulates, which is our next, let's call it our next unit. We had 5 lessons on definitions. We're going to move on. In our next lesson, we're going to start Euclid's postulates. But for right now, those are the definitions. So spend some time, get comfortable with them, see what you can do. I will go ahead and now I will actually upload this whole PowerPoint to our classroom as well. So you have access to the PowerPoint. You can review it, go in and play with it as much as you want. All right. Have a good one today.